Okay, so on to the second lecture on the divergence theorem, which is also called Gauss's theorem. And the first lecture, what we did was we developed the theory. At least we gave a justification as to what the Gauss's theorem was, the divergence theorem was, and that's presented in this page here. And what we're going to be doing in this lecture is we're going to be doing some examples related to the divergence theorem. So the basic description of the divergence theorem shown here in R3 is that you have some sort of a volume in R3W, and we call dW is going to be the boundary of that volume. It should be a closed surface, which I'm also going to be denoting by S. And what the divergence theorem says is it equates to different integrals, and this integral over here is the flux integral over the flux of F, which exits the surface, and the integral on the right hand side gives you an integral over the interior of the surface over W, and this establishes this relationship. And in order for this to happen, we need our function to be sufficiently differentiable. So F has to be of class C1. That means that the first derivative is continuous, and you can see that the first derivative is needed over here. Okay, so we are now ready to go to some examples. So the standard examples that you'll often see in textbooks, for example, would be questions like this, which they'll ask you to verify the divergence theorem for, and then they'll give you geometry, and then they'll give you a certain function, and then your task is to verify. So verification means that you have to calculate this, and in order to calculate this, you use all the techniques that we've studied in the past about calculating flux integrals. So it's a certain type of surface integral where you do a parametrization of the surface and so on and so forth. And then you also need to calculate this, which is a triple integral of a certain function. So if you're given questions of this sort, what you're actually being tested on is those two concepts, whether you can calculate flux integrals and whether you can calculate these triple integrals. And you're not so much concerned about the fact that the divergence theorem tells you, look, there's this really nice connection between them. And because of this, I really don't see the point of doing any examples of this form. So I want to instead do examples which highlight what the divergence theorem actually tells you. So let's look at a simple example. So I have a function here which is given in this particular way, and you can see that this function is it's differentiable. There's no problems with this. So the divergence theorem is going to apply if I want to apply it. And what you're asked to do is that show that the flux of F exiting any closed surface is 0. So it says any closed surface. So if it's any closed surface, you can't use these ideas of parametrizing surfaces and so on. So that's a hint that you probably need something much more powerful than that. And the divergence theorem is what you want to use in this case. So here's a surface. It's a closed surface. And what I'm going to do is I'm just going to apply the divergence theorem. And the divergence theorem just tells me that this flux, which is what you want to calculate, is given by this over here. And this is an integral over the interior W of the surface S. So what can I do? Well, I can actually calculate the divergence in this case. So the divergence would be the x derivative of this plus the y derivative of that plus the z derivative of that, and that's what I've written down here. And these are easily calculated because I'm going to get a 2 from this, I'm going to get 0, and I'm going to get -2. So if you add all these things together, what you get is 0. You just get a big fat 0. So you have the integral of the function 0 dv, and the integral of the function 0 over any domain is just going to give you 0. So you're done, right? So, and S was just any arbitrary surface over here. So that's an easy example of this. Let's look at another example, a little bit more complicated. We have a slightly more complicated vector field G, and you're asked to find the flux of G which exits a certain surface. And this is the cylinder which is bounded by these curves here. So you got x squared plus y squared equals 1, which would be a circle in the xy plane, but in 3D, that's actually going to be a cylinder. And the cylinder is capped by z equals 0 and z equals 1. So here's the picture of the cylinder. Okay, so what you're asked to do is to calculate the flux. So you want to calculate G dot ds across the surface S, but the S consists of, well, 3 different things. There's the top, and then there's the bottom, and then there's the curved surface. So if you're actually calculating this, you need to parameterize those 3 surfaces separately and go ahead and do those calculations. Well, you can do that, but that's really not what I'm going to do here. What I'm going to do is I'm going to I'm going to just continue on by applying the divergence theorem, because possibly that's going to be easier. Okay, so what happens when I apply the divergence theorem? So the divergence theorem tells me that I can replace this with the divergence of G integrated over the volume inside. So the divergence of G, I've taken a shortcut here and I've just calculated that directly. So it's going to be the x derivative of that gives me a 1, plus the y derivative of that's going to give me a 4y, plus the z derivative of this, and that's just going to give me a 3. So what I see is that I have the function 4 plus 4y. So the function 4 plus 4y, I can split this into two integrals. So one is the derivative, is the integral of the function 4, and one is the integral of the function 4y, and I've split that into two. Okay, so now what I have to do is I have to figure out these values of these integrals. This one is actually easy because this integral is just telling me, well, it's just a volume of W, the volume of W, and this is a cylinder. So W is a cylinder, and we know how to write down the volume of the cylinder. That's fairly easy. So here's my 4. I put down the 4, and then I've got a pi r squared times h. Yeah, the radius is 1, and the height is 1 as well, because it's between z equals 0 and z equals 1. So that's done. Okay, what about the second integral, this thing over here? Well, this actually turns out to be easy as well, but because of a different reason. Because if you're looking at this volume that we have here, the volume is completely symmetric around y equals 0. Y equals 0 is the xz axis. So if I slice this with the xz axis, I have a perfectly symmetric volume that I'm looking at, and the function y is anti-symmetric across that. In other words, it's an odd function. So wherever you see a positive value for y, you're going to see equally a negative value for y. So when you're doing an integral and adding all these things together, everything's going to cancel. So it's an odd integrand over a symmetric region. So you're just going to get 0, which means that your answer is 4 pi. Okay, so you're done. So the value here is 4 pi, and in this case it was much easier to use the divergence theorem than to actually calculate the flux in this way directly. So this is one of the advantages of the divergence theorem. So you have a tool which enables you to come to transfer between certain types of flux integrals and triple integrals over the interior, and in some cases one or the other of those might be easier to calculate, and then you can just use that as a technique. Okay. Next example, I'm going to think of this as a thought experiment. Now, I mentioned when we were deriving the divergence theorem that the divergence theorem is actually valid in Rn, where n is just anything, right? So what I want to do here is I want to look at the divergence theorem in R1. The previous two examples were in R3, which is the sort of natural environment in which you can do that. So between the blue lines over here, what I've written down is the divergence theorem in general in Rn. So f is some function which goes from Rn to Rn, and then we can calculate the divergence. There's no problem in calculating that. And then if you take W to be some general volume in Rn, so what you're doing here is you're doing a volume integral over a volume in Rn. So there's actually n different integral signs over here. What about on the right hand side? On the right hand side, you have your integral over the boundary, and the boundary is going to be one dimensional less. So you're going to have n minus 1 integral signs over here. And then that's going to be a closed surface which encloses the volume n. The volume W. Okay, so what I want to do is I want to sort of reinterpret this in R1, right, where n is equal to 1. So first, let's look at the geometry. So we're looking at a W. So W is a general volume in Rn. So R1 is just this line over here. It's just the x-axis. That's all we have. So we can't go anywhere outside the x-axis. So if I'm thinking of a volume within quotation marks, so what I'm thinking of is some space-filling object. And that would be something like an interval would be your generic volume in R1. So the green set is going to be my W. Okay, so then what about my boundary of W? So if I'm in W and I want to exit it, but remember I'm only in R1. So I mean in this space, if I want to exit it, well, I have to jump out from this point, or I'll have to jump out from this point. So A and B, these 2 points A and B are actually my boundary. So my boundary consists of 2 points. That's it. Yeah, so it's just those 2 points. So that's a geometry. Okay, now what about a function? So in general, the function f went from Rn to Rn, but if n is equal to 1, it has to go from R1 to R1. So my input variable can only depend on x, it can't depend on y, z, and so on and so forth. And my output has only one component, and that's component I'm going to write in the x direction, right? So I'm just going to put a vector I over there. So here's our general form of a vector field. Which is sort of in R1, and we're going to assume that this function is differentiable because that's the condition that we need in order to apply the divergence theorem. So let's see. So what I'm going to do first is I'm going to look at this left hand side and see what this becomes. So I have to do an integral over the entire volume, but what is my volume? It's just this green area over here. So that transfers to an integral from A to B. Okay, and this is a general volume element, but my general volume element in R1 is I'm going to be picking these little tiny volumes, and that's actually dx, right? So that's fine. What about the divergence? So if I'm calculating divergence, here's my function. I need to take the x derivative of the x component. That's going to give me f prime of x. Then I need to take the y derivative of the y component. Doesn't exist. Z derivative of the z component also doesn't exist, and so on, right? So all I just get is I just get f prime. So the left hand side of the divergence theorem just gives me this expression over here. What about the right hand side? So let's look at the right hand side. I have to calculate f dot ds. So this is a flux exiting the surface. So it's an integral over these 2 points. Right, so an integral over 2 points. Now, integral, remember, is sort of like an addition. It's a summation. So let's see. So over here, what I need to do is I need to look at the value of f, and I need to look at the value of ds. So f at that point is, well, it's given by this, right? So it's going to be f of b times I. Right, so there's my f. But what about my ds? So ds has to consist of an outward pointing normal, and that's why I've drawn this outward pointing normal in pink in this direction. It has to be pointing out of w, so that's in the direction of positive I. So I'm going to put a positive I over here for ds. So I claim that ds is equal to positive I at this point. So there's a little there's some sort of subtleties over here, because when you talk about this vector ds, there's a certain magnitude to this in addition to the direction, and that magnitude in this case relates to the size of your sort of surface element, whatever that means. But you're in 0 dimensions over here, actually, right? So I'm going to think of that as a 1. So this is a very subtle issue, and if you want to understand this further, you need to talk about measure theory. So measure tells you how you attribute a size to certain sets in certain dimensions. So ds, for the purposes of this, let me just say that ds is equal to I, because it's the outward pointing normal. And then I have this point over here, and I have to do the same thing. So I have to evaluate it at a. So I get fa times I, but then I need to have the outward pointing normal, but the outward pointing normal is in the opposite direction, right? Because I have to be pointing out of my set w. So I'm going to get I'm going to get a negative I in this case. When I do this calculation, of course, that's quite easy. I dot I is 1 and I dot negative I is negative 1. What I get is f of b minus f of a. So what have we discovered? You discovered that these two highlighted things are equal to one another. And if you look at that, you realize, well, this is the fundamental theorem of calculus for single variables. So the divergence theorem is a generalization of the fundamental theorem of calculus to Rn, basically, or if you prefer, the fundamental theorem of calculus is a special case of the divergence theorem. And indeed, if you specialize the divergence theorem to R2, you get another really important theorem, a theorem that we've talked about, and that turns out to be Green's theorem. That's a little bit more complicated to understand than this, but I have given that as a practice problem. Okay, let's do another example, and this example is now more related to physics, and this is called Gauss's law of electrostatics. Now, the divergence theorem is also associated with Gauss's name, and that's because Gauss was both a mathematician and a physicist, and he was probably motivated by some of these physics concepts to come up with the divergence theorem. So Gauss's law of electrostatics says the following, right? So suppose you have just any old surface, any closed surface in R3, and then the electric flux which exits that surface, right? So E here is the electric field. So it's the flux of that of that vector field which exits the surface is proportional to the charge which is contained within that surface. So you might have a whole bunch of positive and negative charges like electrons and so on and so forth. So it turns out that the electric flux which exits that is proportional to the charge which is enclosed by the surface, and the proportionality factor has this 1 over epsilon naught, which is called the permittivity. Okay, but this is true for all S. So this upside down capital A here means for all. This is true for all closed surfaces S. So this is Gauss's law of electrostatics. So we're going to analyze this just a little bit further and take advantage of the divergence theorem. So the first thing that I'm going to do is I'm going to replace this charge enclosed in terms of an integral. And how can I do that? Well, I'm going to define a charge density. That's the amount of charge per unit volume, and that's going to be rho, which is a function of x, y, and z. So it could vary. So you could have lots of positive charges over here, for example, lots of negative charges over there. So rho, it depends on location in space. And then when I take rho and I dv and I do that triple integral, that's going to give me my total charge. Yeah. So my charge enclosed is going to be given by this integral over the interior. yeah, over the interior, which is W, and then I've got this proportionality constant epsilon 0 as well, epsilon naught as well. If I apply the divergence theorem now to this left-hand side, I can rewrite that as the divergence of E dV, and then I have this expression over here. And what's really nice here is that both are over the same volume and dV, so I can combine those together, and I got this statement here. What's quite nice about this statement is that because this Gauss's law of electrostatics, as given over here, is for any surface S, any closed surface S, this statement is true for each and every volume W that I care to choose. So for all W that I care to choose, this is true. Let's look at this this function that I have inside the integral. And what this is telling me is that if I integrate this function over each and every single volume, I'm always going to get 0. So the only possibility then is that this has to be the zero function, because if this is not 0 at some point, if this is positive, for example, at some point, if it's positive at this point, let's take a tiny volume around it, so it's going to be positive around that, and then when you do this integral, you're going to get something positive, right? So the only way in which this can be true for all volumes W is if this function is identically equal to 0, which tells you then that the divergence of E has to equal rho over epsilon naught. So what we've discovered there is actually one of Maxwell's equations. So Gauss's law is one of the 4 Maxwell's equations. So here's Gauss's law in the integral form, and what we've discovered is that we can rewrite it in this form. And then this is called this is a differential form of the equation. So typically what you have is you have a certain charge distribution, and what you want to do is you want to figure out what the electric field is. So this guy is the unknown, and everything else is known. So if you look at this equation, what you have is an integral equation to try to figure out what E is, and these are typically very, very difficult. It's a much more difficult concept than a differential equation. So you can only solve this typically if you have some very nice sort of situation. Whereas the second equation that you see here is a differential form, and that there's a much greater technique suite of techniques which are available for solving differential equations. And I should mention that these are the electrostatic versions, so there's no change in the charge. If there was if the charge was changing with time, if there was a current flow, for example, then there's going to be a magnetic field associated with this. So these are the Maxwell's equations for the static situation. Okay, so that's a bunch of examples related to the divergence theorem.